How are you all doing this morning?
Doing pretty good. How about you?
Doing all right. So today we are going to be playing around on electric a bit more before we jump into talking about differential amplifiers. So let me share my screen. Close that. I gotta get things up. Share screen. Electric. Alrighty. So couple of things. Let's see. A big one is that I figured out what the problem that I was having the other day and why my currents and all that kind of stuff didn't match. One thing I guess I was just having the biggest brain fart in the world. So when I kept putting those other transistors and attaching them in parallel, that was just making this transistor larger and larger and larger. So obviously, 3 10x2 transistors in parallel should be the same as a 30x2 transistor. I was just counting the widths incorrectly, so I would like to explain that really quick, and I feel like an absolute jackass for screwing it up. But effectively, we're just counting the width along the side of our gate here. So this is 10, and then over here we have, this is the shared drain between, the shared source between these two transistors. And so we have 10 on this side and 10 on this side of our gate. So that's why it's 30. Another very dumb mistake that I made was that I was only considering, when I was looking at the model there, I was only considering the current through one of these 3 parallel transistors, which is obviously not going to be the same as all 3 of them combined together from Kirchhoff's current law. So I've got it set up now, how we had it the other day with the right number of transistors. And if we look at our resistor currents, tools, right spice deck, so if I look at the current through my 2 resistors, that is not what I wanted. There we go. And the current through my other resistor. We can see that they're pretty dang close. They are within half of a microamp of each other, and that's good enough for me to consider them effectively being equal. So we can see that resistor 2 one is negative 74.12 microamps, and the direction of that current doesn't particularly matter. And then the other one is negative 74.54. So it's like 0.4 microamps off. So that's good enough for me. Yes. Let's see what's going on in chat. Dang it. Thank you for letting me know that, Diego. Here's LT Spice. There we go. All right, are you guys seeing LT Spice now?
Yes.
Okay, great. So, 0.4 microamps, that's good enough for me. So what I have gone ahead and done, let me close this out, is I have made a new version of this exact same library. I literally just copied that over, and then I put my 3 transistors in parallel inside of a guard ring that's tied to VDD, and then wired up my transistor accordingly. So I'm going to give you guys a couple of minutes to finish up effectively your cascode current mirror, and then we'll run a simulation. You don't have to use the 3 in parallel thing like I did. I just chose to do that so that I can make things a little bit more compact. One thing that I do want to point out though, if you do choose to use a guard ring like this, as opposed to just a simple body P-well body connection, or excuse me, an N-well body connection. It's an N-well body connection because the PMOS transistor sits inside of an N-well. The minimum width for the N-well connection is 12. So when you put down your contact, like, let me show you. If we put down an N-well contact like this and we make it, let's say, 20 long, if I press F5, I'm going to get an error. And that error says that the width is less than 12 wide. It's currently 11. So I can fix this simply by changing my X size to 6. So I've made it a little bit wider, press F5, and now I get no errors. There's also some issues with the spacing of the these wells that are at a different potential than VDD to these active regions. So that's why the ring for my PMOS transistor is a little larger. It's just I'm trying to make it as small as possible, but not getting any errors. So this guy is a 6x55, and this guy is a 6x75. So anyway, I'll give you guys a couple of minutes to catch up to where I'm at here. And if you have any questions, feel free to ask. Or if you need me to zoom in on anything or anything like that.
Dr. Hartman,
Yes, sir.
getting a lot of errors when I try to put my my PMOS components close to each other.
Let me see something real quick. I'm trying to figure out how to let everybody share so that you can share your screen with me so that we can look at what's going on.
I can't. I'm on my my desktop and my laptop, so I'm not in the Zoom meeting on my electric.
Okay, well, I mean, you could always join it twice. That's what I was doing the other day before my desktop decided to not open electric. But so describe the errors that you're getting then, I guess. It's gonna be really hard to fix if I can't see them.
Just a spacing error.
Okay.
I was having it yesterday mainly as my problem. I was just wondering why it wouldn't, like, I couldn't put them together.
So you're having issues, it's giving you an error because you're placing 2 PMOS transistors too close together?
Correct.
All right, let me see if I can try to replicate that. So I've got a PMOS transistor and another PMOS transistor down here. Nothing. Is it giving you something like that?
Yes, but it looks like it might not be doing it anymore. I don't know.
Oh, well then, I don't know.
Yeah.
I mean, the reason why it's giving you that error is because you have 2, or the reason why it's giving me this error is effectively because I have those two active regions and they're too close to each other because these guys aren't connected. But as soon as I tie them together,
It's good.
the error goes away. So you may have forgotten to attach, like my best guess. Let me do this again. Like this J. Let's make this a 10 by 2. Another guy out here. 10 by 2, and we'll rotate it 90 because I forgot to do that when I put it down. And throw a P active there in the middle. It's going to be 10 in the Y. So if I move this guy over like so, but forgot to actually connect the active region on my contact to the active region on my transistor, it's going to give me an error telling me that I have those two things overlapping. And again, that could be resolved just by connect. Oops, I don't want to do it to that side though. That would be bad. And now the error is gone. So it's pretty easy to accidentally forget to make all the little connections that have to happen.
Okay, I'm sure that's probably what happened. Try to fix it.
Yeah. Another thing that I've done, I guess maybe I should mention this. You can't really see it on the drawing, but I've gone through and I've renamed all of my transistors just because with 8 transistors, 3 PMOS, and or I guess 7 transistors, 3 PMOS transistors technically forming one larger PMOS transistor, and then 4 NMOS transistors. It was getting a little cumbersome trying to remember what was what. So I just went through and I labeled, so my PMOS transistor has an M5A for the leftmost one, M5B for the middle, and M5C because we labeled that transistor M5 in our original diagram. And then down here, so this transistor is M2. Sorry, this one is M3. This one is M1. This one is M2. And this one is M4. And I've just gone through by clicking on it, pressing Control I, and then giving it that name, just so when we try to find the signals that we're looking for in LT Spice, it's a little less cumbersome.
Another question.
Sure.
So for the metal 2 to metal 1 contact, the little purple square, does that just float on top of the metal 1 to poly contact, or does it connect somehow? I couldn't figure out how to make it actually connect.
All right, so you're talking about this guy right here?
Yes, sir.
All right, so let me move it out. Oh, that was terrible.
So it is connected.
Yes, it is connected. And so what I did there is I dropped my contact off to the side. So I'll just replicate it right here. So I put my contact down, left clicked the contact, right clicked over here. So it has the metal connection. And then I slid it over on top.
Gotcha.
And now I'm connecting to that metal.
Okay.
Yeah, that's one of the issues with stacked contacts. It's hard to see that there was a poly to metal 1 contact underneath that metal 1 to metal 2 contact.
Yeah, I was sure they weren't floating, but I couldn't figure out how to do it.
How to connect it when you put it directly on top, yeah. So I put it off to the side, connect it, and then slide it over.
Gotcha.
Dr. Hartman, can you remind me why the ring around both transistors?
I'm sorry, Diego, I'm having a little bit of trouble hearing you.
Could you remind me what's the use for the ring around both MOSFETs and
Sure. So this bottommost ring, as we can see, it's tied to ground. And so what this ring is doing is it's serving as the body for, or the connection to the body for all of these Nmos transistors down here. So the issue is that if I don't have a body connection, then the P-well that my Nmos transistors are sitting in might not be biased at exactly 0 volts, right? Because and so this is just forcing the region of space around all of these Nmos transistors to be at exactly 0 volts so that I don't have body effects. And I'm doing the exact same thing with this ring up here, except that my top ring is a N-well connection because my PMOS transistor sits inside of an N-well. And I'm saying explicitly that I'm tying this big region to be at 5 volts so that my N-well transistor doesn't suffer, or should be from, so my PMOS transistor also doesn't suffer from body effects. I actually think, and I'm going to try something out here and see if it gives me a horrifying error. I'm going to make sure. So when you drop pure things on your schematic, which I'm double checking something here, but you need to make sure that this easy to select box is selected, because if you don't, you can't actually select it again. So I want to see if this is going to give me an error. Give me 2 errors. So what's going on? N-well is less than 12 wide. It's the same thing. So what I'm going to try to do is actually, let's make this, let's see, 60 by 40. No errors. So I've explicitly defined this whole entire region to be one large N-well. And I bet now that I've done that, I could make it my ring slightly smaller, but I'm not going to go through troubleshooting all those errors that are going to come about from that. The reason why I did that, if we look at the drawing right here, there is effectively blank space between this bit of N-well that's my guard ring connection, and this bit of N-well that is where my transistor is sitting. So if I put this in, this whole big box is then N-well, and by putting that 5 volt potential on my guard ring, I'm saying this whole big thing will be at exactly 5 volts to avoid body effects. Did that answer your question?
Yeah, that makes a lot of sense. Thank you so much.
Yep. I'm going to step out for just a moment to use the restroom. I'll be back in like 2 minutes or 3 minutes. All righty, how are you guys doing?
Dr. Hartman, I had a question. What's your dimensions on the PMOS body ring?
Okay, so I am using for the vertical members there, they are 6 by 55. And for the horizontal ones, they are 6 by 75.
All right, gotcha. Thanks.
Yeah. After class, I may go through and see if I can make that ring smaller now that I remember to put that big chunk of N well in the middle. But for now, I'm just going to leave it like this.
Okay, Dr. Hartman, I restarted on the putting the transistors together, and I think I'm getting the same error, so I will screen share now if
Okay.
you
Let
let
me
me.
stop sharing so that I can figure out how to do that. Let me press this. Advanced sharing options. All participants may share. And all participants may start sharing. Okay, you should be good to go.
Okay, it shared and also muted me. So
I saw the screen share. I didn't see the
Okay.
mute, or I couldn't hear anything, but I
Yeah.
also don't see your error window at the bottom. Do you
Okay.
guys see my error window when I'm sharing the screen?
Yeah, I don't know how to make it like, so if I hit F5, it'll like do it, but then I have to minimize this window, and I don't know if you can still see that. Then
I
it
can
comes
see
up.
your messages now, yeah.
I don't know how to dock it though.
Well, yeah, I mean, the way that I have mine set up, I just manually made my layout screen smaller so that I could see the messages screen. All right, so
Okay.
you got 10 errors, so press the greater than key. Maybe press 5 again, or F5 again, I'm sorry. Or press it with with the cursor somewhere in the layout window. So like click in there.
Yeah.
All right. Press F5.
All right.
All
Okay.
right. So it is complaining about your notches. So slide that contact over to the, yeah, keep going until, yeah. And it's gonna slide that guy over.
See, this is already an error.
Yeah.
I get the same thing, but if I press F5, it says 0 errors.
Mine gives me like all kinds of errors.
Okay.
So the errors that you're getting is because of the size of those notches effectively. Keep sliding that second transistor to the left. That's too close. Because that big rectangle is the gate. All right, a little bit more to the left, like 2 or 3 units. Stop there. So that's, you could probably slide it over 1 or 2 more grid spaces and still not get an error.
Even though it's saying error, like when I'm holding it.
Yeah.
Okay.
Now slide that guy over. Slide him over. Yeah, and you could, let's see. Why do you have 4 transistors? Delete the one on the right. Hit F5. 0 errors. So it
Okay.
was all about those notch runs. So effectively, it was saying that the run between the two pieces wasn't wide enough. But when you overlay everything like that, it gets rid of it.
Okay. I was driving myself nuts yesterday trying to figure that out.
Yeah, your middlemost transistor could technically be slid like I think half a grid unit over to the left still, but then you'll have to slide everything else too. Now that, yeah, nope, you still got your transistor grabbed. So you're about to
Oh,
put
yeah,
your
right.
on top of that metal contact.
Okay.
Still got it. So you press mouse over that and press control and then click on it. Now you got it.
Is there a way to use the arrows with this, or do you have to always click and drag?
I don't know. I've always just clicked and dragged.
Oh yeah, arrows work.
Oh, well, that makes things actually significantly easier.
So
All
I'll
right,
stop
and then you
sharing.
need another one on the right. But yeah, okay. So,
Okay. Thank you.
yep, not a problem.
Dr. Hartman.
Mm-hmm.
So on my PMOS, they're giving me an error of a notch layer-ish error.
Can you?
where-
Are you willing to show me? All right. Press the, okay. So this is something that I was having earlier too. So what I want to see if this would have fixed it. So go into components, click pure, click, let's see, NWell node. Click on it. Now press Control I before you click off of it and press easy to, yep, there we go. And then make it like 60 by 40. And then drag it over in the middle. Now press F5.
Yep, all good now.
Yep, that's what I thought. So I bet, like I said, I think that PMOS guard ring can probably be smaller. The issues that I was having was that I forgot to make it end well all the way in that region.
Right, a giant thing of NWell for everything to sit in.
Yeah, so the issue it was having is it's effectively saying, well, you have this thing at NWell over here, and it might be at a different potential than this other piece of NWell, and the width of the P well between it was too small. But if you make it the whole thing NWell, it's like, oh, I understand what's going on now.
Great, thank you.
Yep. Yeah, so like down here on our Nmos transistor bit, it's not giving us that error, even though there's a little bit of gap here. Like you can see there's nothing in here, but it's because the substrate is implicitly P-well. So it's considering that this region right here is P-well. This thing on the side of the ground ring is P-well, and although it doesn't show it, this is also P-well, so that's why we're not getting that same notch error. If we wanted to convert our design to a non-C5 process, it would probably be good practice to explicitly put a big chunk of P-well inside that ring, just like we did N-well for the other one, to make the design transferable between technology nodes. So Let's do another 60 by 40, I think. Might be too big. Yeah, so we drop that guy in, and F5, still no errors. But now we can explicitly see that that entire inner region of the ring is P-well. Not required, but not a bad idea either if we wanted to use a non-C5 process. Excuse me. Goodness gracious. All right, so we getting close to finishing up that topmost bit.
I hope so. I'm still getting a lot of errors, so.
Show me what's going on, Grant.
All right. All right. Can you see it?
So the issue I think that you're not connecting, it's connecting the active regions and not the metal.
Okay. Of the grounding ring.
Yes,
Okay.
that would be my best bet. Yeah. So, no, what I mean by that is, you probably can't see my mouse on your screen. Yeah, delete those little green bits in between things.
Okay. And so,
Select that, sure. Left click, right click,
okay.
connect by metal. And if you don't stack your contacts
It'll have it
exactly
run.
on top of each other, you're going to get another error. And it's because the size of a contact is defined to be exactly, I think it's 2 by 2 or 1.5 by 1.5. So like right now, if you hit F5, you'd get an error
Gotcha.
because your contacts aren't directly on top of each other.
So if I do this, you think I would be okay?
If you were so you see how so you're going to get at least 4 errors just based on the size of your contacts.
Okay.
So that bottom, yeah, take your bottom piece, that guy right there, and move it down 1 and to the left 2. All right, take that guy, move it, there we go. That guy, move it down. Now press F5.
Only 8. That's pretty good.
Only 8. Okay. Now go to pure.
To what?
Pure in the top left. P-U-R-E, yeah, and click on Nwell. Goodness gracious, I got something caught in my throat.
Okay.
Drop it down there, wherever, doesn't matter. Press Control I.
I don't know if you can see.
I can't see that, but just make sure the box that says easy to select is selected.
I
All right, so you got a square ring, so try, I don't know, 40 by 40 for the dimensions.
easy to select would be in more probably, huh? Okay. Cool.
Yeah, I think so.
Yeah, I found it. Okay. So do what?
Now, click that piece that you just dropped of Inwell and make it 40 by 40. So hit Control I and change the dimensions to 40 in the width and 40 in the length.
All right, and put it
Now
underneath
drop it in
everything.
the middle. Yep.
Okay.
Now press F5.
6 errors.
All right, now let's see what these errors are.
Okay, so we would do shift greater than. So this
All
is
right,
too
so
close.
it's saying that those two things are too close together. So just grab, you're gonna, move that chunk of N-well out of the way, and then grab everything and move it over a little bit. Yeah. Now press F5.
Only 2.
Move that metal piece. Just the metal piece. Hit Control and
Control.
click until you select that metal piece there.
Yeah, it's not like.
You have to click. Like you have to Control and left click. And keep holding down Control and left click until you get that.
Okay.
Slide it up. Hold on just a second, I need to do this. All right, so you get rid of all your errors, Brett?
Yes, sir. All gone. Thank you. I think your mic's messing up, Dr. Hartman.
I don't know.
Oh,
why
it's just stopped. Okay.
it was doing that.
The
when
exact
I
same
was
thing that
doing
happened the other
circuits
day
yesterday,
when I was
or-
telling you about it. I'm not
Yeah.
sure, but
It kind of sounds like you're in a heavy metal band for a little while and then it stops.
Well, it's unfortunate that it stops then. Alex, how is your transistor stuff going? I haven't heard anything from you today.
it's going okay. I had a couple of the issues that I think Aiden was having, but what you said fixed them. So
Cool deal. Mitchell, how's yours?
I'm finishing up the grounding ring on the top one. It's going on.
It's going, yeah.
How's yours coming, Dr. Hartman?
Mine's done. That's why
Good.
you're looking at it. I mean, I can play with the dimensions if you guys want, and then make everything that you've done. I mean, the dimensions for your grounding ring don't have to match mine by any stretch of the imagination. Alrighty, let me guys know when you're ready to simulate stuff.
I'm all good if everybody else is. I'm not sure if other people are still working or not.
I'm good to go too.
Right. Diego, Grant.
Yeah, you can start.
All
Yeah,
right.
I'm good to go.
Okay. I'm gonna assume Mitchell and John are good too then. All right,
Go ahead.
so let me zoom in on this spice text here. And let's start with not this voltage at 3.9. So I want to show you something. So I'm changing the voltage, excuse me, that I'm applying at the gate of the PMOS transistor to 4 volts. I've got 5 volt DC supply. I'm letting, I'm initializing the drain source voltage 4, so that's effectively my output voltage for this current mirror at 0, and then I'm scaling it from 0 to 5 in 1 millivolt increments and all that kind of stuff. So let me move this out of the way. Tools, simulation, right spice deck. All right, got to remember to stop sharing, start sharing LT Spice. And we're going to look at the currents, the drain currents for transistors M1 and M2. So ID M1, no, not IS. Why is it being, well, screw it. I'll type it in because this will be better or faster. So I'm getting around 5.5 microamps, which is not really what this thing is designed for. And the reason why I'm only getting 5.5 microamps is because I'm not actually pushing that transistor, that PMOS transistor, really far into saturation, right? So the threshold voltage for the PMOS transistor is going to be 0.9 volts below VDD, and I'm only 1.1 volt beyond that, where my VD sat for these guys is about 250 millivolts. So if I close this out, jump back on LT Spice, and I change this to that VGG to, I had it at 3.9, let's try 3.85 and see what happens here. That would be exactly 250 millivolts past the threshold voltage, and hit OK, and then simulate it again. ID M1, ID M2. It looks like I'm a little bit past where I need to be, right? So my reference current isn't quite 20 microamps now, it's 25 microamps. So we've gone past it ever so slightly. Close this out. And share screen. What we're doing is effectively we're iteratively finding out exactly what voltage we need to bias this PMOS transistor at to get our reference current of 20 microamps. So I'm going to try 3.88 this time. and simulate. And we're pretty much spot on at 20 microamps. I'm going to change this guy, make it negative so that we're looking at it in the same direction. And yeah, so we're just under 20 microamps, which if you recall from our, let me close this out real quick. If we went to our resist, can you guys, let's see, I'm not sharing my screen, share electric. So if we looked at our single current mirror with a PMOS, or with, excuse me, our non-cascoded current mirror with a big PMOS transistor acting as our resistor, when we simulated this guy, add traces. I want the current through my PMOS transistor. So our reference current is just around 19.5 microamps. So we're pretty much spot on to where we are trying to be. Close this again. Share electric and go back to our current mirror. So our current mirror, we have the correct bias voltage for our PMOS transistor, and we'll shortly work on how to create a circuit to generate that specific bias voltage to make sure everything is correct. But this is looking pretty good. So to this point, we've done everything on our layouts, right? But there's another big section of our modeling, which is modeling our schematic. So let's go to the Explorer bit here. Make sure we're in our ELEN 438_211 library and create a new cell. And I'm going to call this cell Nmos _cascode_ current. I'm naming it the exact same thing as I named the other one. I'm making a schematic instead of a layout. I can't see the full name, so I need to change it to current mirror. Okay, and then actually, I'm going to delete this cell and rename this one. All right, so now we should see, make sure I got the right thing. So now instead of just having a little yellow dot, now because these two guys are named the exact same thing, they become their own submenu. And what that's going to allow us to do is do layout versus schematic checks and all that kind of stuff. All this is really doing is just making sure, this is another layer of security of making sure we're designing our device correctly, because we're probably more familiar with working with the schematic diagrams for analog electronic circuits than we are by looking at a layout and saying, oh yeah, those those 3 PMOS transistors right there in parallel are acting as one big PMOS and all that kind of good stuff. So we're going to play around with some schematics now. So I've selected my schematic cell, and I'm going to go into components, and it's an entirely different window. We have lots of options here for some digital things. If we mouse over, this is a box, an XOR gate, multiplexer, AND gates, OR gates, buffers. We got some flip-flops, all that kind of stuff, switches. And then we have our transistors and all that kind of stuff. And that's where we're going to be spending most of our time, is putting in transistors. So we have a basic Nmos transistor. And if we click on the arrow, we got lots and lots of different options. I'm honestly not even entirely sure what the majority of these do, but this is allowing us to switch from NMOSs to PMOSs all the way down to BJTs and JFETs and all that kind of good stuff. If we select this guy, this is the one, I think, let me see. Let me pop this guy in and zoom way in, yeah. So I believe this is the this bottom one. So I think this is the 3-terminal MOSFETs, and this guy right below it, yeah, is the 4-port transistor, and that's what we want because we have a specified body connection that we're going to concern ourselves with. So on these transistors, there's lots of different little places that we can select. I'm going to try to scale in here so we can see things. Is this, all right, hold on. I want to make sure I'm selecting the right thing. So just to be clear, dropping an NMOS in here, and it's got the arrow pointed towards the gate. If we press Control-I, we pull up the menu. So this is an NMOS transistor, so we're going to make this guy transistor M1. It should be a 10x2 transistor, and I'm going to press Apply. And then I'm going to Control and Shift click until I get that text, and I'm going to move it out up here. And the reason why I'm going to do that is when I need to also set its spice level, and I don't want that text sitting on top of itself. So set spice model. This should be an NMOS, excuse me. And I'm going to drag that over here. So as we click on the various pins of this, and it may be hard to see, that's one of the things I'm trying to show you guys. So when I click on the gate pin, it puts a little dash that lets me know that the gate is selected. When I click up here on my drain, it looks like a little plus sign that lets me know that my drain is selected. When I click here on my source, there's a little plus sign. And then when I click here at the body, it puts a little dash there to let me know that my body is selected. So to make this match the schematic that we drew like on paper or whatever on whatever day it was, when today's Thursday, so Tuesday, I'm going to mirror this guy. So I have a 10x2, and then I'm going to make another one of these. Drop them up here, And I'm going to call this, so it automatically incremented it to not be M2. It's calling it, or excuse me, not be M1, it's calling it M2, but this should actually be M3. And then I'm going to tie the drain of transistor M3. So I left click the drain, and then I right click on, or excuse me, I left clicked the source of transistor M3, and I right clicked the drain of transistor M1, and that put my, that connected those two nodes together. I'm going to give myself a little bit more wire here out in this direction. I'm going to take another one of these transistors, and I'm just copying and pasting. I'm going to mirror it. So I go to edit, mirror, left, right. This guy should be M3 or M2, I'm sorry. I've tied the gates together as they should be. Make another copy, drop it up here. This guy is supposed to be M4. The gates of M3 and M4 should be tied together. The source of M4 should be tied to the drain of M2. I need to put a wire here, like so. So now I've tied the gate to the drain for transistor M1. Give myself some wire. I've tied the gate to the drain for transistor M3. I'm gonna, now I've got M4 selected, the drain specifically, and I'm just gonna run a piece of wire here. And with that little dot connected, I'm going to export VDS4. That is enormous. And I can move that text up here, but it did not move. So I moved the text, but I didn't move the export. And we can tell that there's an export because of that box with the plus sign in it. All right, so now I got to put my PMOS transistor in. So I need to make sure that I have the 4-terminal PMOS transistor selected. Just going to drop it in like so. Tie that together, move it down a smidge. All right, some wire up here. So on the left-hand menu, well, actually, hold on. Let's look at this PMOS transistor real quick because that's not what I wanted to do. Let me disconnect it. Disconnect it there. So I have a 10x2 PMOS transistor, or it will be a 10x2 in a moment. I'm going to label it as M5A. Select my text, move it out. So my MOS transistor is actually made of 3 of these guys in parallel. So I need to make sure that that is how I set this up too. So this is going to be M5B. It's going to be M5C. I'm tying my gates together. I'm tying my sources together, and I'm tying my drains together. So that these three PMOS transistors in parallel will be treated as a single PMOS transistor. I need to set the spice model for all of my PMOSs because I forgot to do it a moment ago. Oh, I didn't have my transistor selected. Tools, set spice model. Tools, set spice model. There. All right, so I'm going to export this pin as VGG because I believe that's exactly what I had on my layout. It is, again, huge. And so the last thing I have to do is power this guy and ground it. So to do the power, I'm just creating another little wire here. So if we look over on the left-hand menu, these two concentric circles, that is our power node. We'll click on the middle and then click to that wire. Hold on, let me delete this guy right here because I think it's going to cause it to be hinky. And I'm going to export that middle pin as VDD. Down here at the bottom, I can just put a ground node, wire it up, put another ground node, wire it up, and I'm going to take my spice code from my layout and literally just copy and paste it into my schematic. Control. Like so. And something that I have not done is all of my bodies connections. So I've ignored them right now. They're all floating potentials. So I do need to go back through and tie all of them to ground. For my Nmos's. So bodies are tied to ground there. Bodies are tied to ground there. For my PMOS transistors, the bodies should all be tied to VDD. All right, so probably would have been smarter to mirror those PMOS transistors. Sure. All right, and so what I'm going to do now is I'm going to simulate, and we'll see if it behaves similarly to how, well, let's see. Found one error. Let's see what that is. An unnecessary pin. Okay, so it's just saying I put a point there that is unneeded, so I deleted it. F5, 0 errors. All right, I've set my splice model for all my transistors. I've got all my body connections taken care of. They're all 10 by 2s, which is what they're supposed to be. So let's see, I'm going to add a trace ID M1, add trace ID M2. Boy, howdy, I'm getting 300.
We're still looking at your
Oh,
electric.
okay, sorry, say, sure, let me show you what's going on here. LT spice. So I'm getting 300 microamps instead of 20. So that concerns me because I must have made a mistake somewhere. So let's see what is going on with electric here. VGG2. So I don't have that voltage labeled correctly.
Oh, we're also still not looking at your screen.
Son of a bitch. Thank you.
You're welcome.
Where did Zoom go? Share screen. Electric. Okay. So I have my gate voltage here on my transistor applied to be VGG, but here I'm declaring it to be VGG2. So let's fix that. Let's see, there's VDS4. All those, everything else seems okay. All right, let's try simulating this again. Let me stop that share. Share LT spice. Add trace ID M1. Add trace ID M2. And our graph looks pretty much exactly the same as we saw in our whatchamacallit, our layout. If you let me make what I'm going to attempt to do is show them side by side. Oh, but you won't be able to see two different windows of LT Spice at the same time because Zoom is dumb. Never mind.
Dr. Hartman,
Yes.
there is an option in Zoom, and I don't know, one, if you have it enabled, or two, how to do it. But when you share, instead of sharing like a specific screen, you can just share like screen. And so we would see like everything you're seeing.
All right, let me see if I can find that because that would have made, oh, I'll be damned. Yeah, it just says screen. So right now, are you seeing LT Spice?
Yes.
Okay. Well, that is awesome. I wish I would have known about that much earlier, but it's all good. So there is our LT Spice graph for our schematic. When I go into here and I do a spice deck, ID M1. So you can see the pop-up windows and stuff too?
Yes, sir. We
Yeah,
can see
we
you
sure can.
switching
Oh my,
everything.
this is how I have to do it from now on then. This will make everything so much easier because you can actually see what the heck I'm doing. Okay, great.
Yeah, and you don't have to switch between like spice and electric either.
Yeah, that would be fantastic. Thank you for that, Grant. Let
No
me,
problem.
I don't know how, well, I do know how. I didn't notice that. I'm wildly unobservant, but yeah, I think this will make our lives much easier. Well, that'll work. So I'm putting this guy up over here, and I need to put this guy. Let me scooch this guy over. So on the left-hand side, we have the schematic version, and on the right-hand side, we have the layout version. And they look pretty dang close. So that's good. We can see like this corner right here. So this plot is as a function of VDS4. That's what our x-axis is. So this corner right here is transistor M2 entering or leaving the triode region and entering saturation. And this corner right here is M4 leaving the triode and entering saturation as we increase that total voltage drop over those two guys. And we get pretty much the exact same thing over here. So I am pleased with the matching between the schematic and the layout there. So the only other thing that we need to do, and I'm concerned that this is going to just start giving me wild errors, but we'll do it anyway. So there is a tool called, where is it at? ERC, check wells, NCC. Schematic and layout views in current Windows. So this NCC, it's a network conduct connectivity check, is effectively the layout versus schematic check for electric.
So is this basically just a way to check that what you're trying to make is actually like connected?
Exactly right. So it's a way to check. It's a way to check to see if the schematic and the layout are representing the same thing other than just simulating stuff.
Gotcha.
And the only conflict that it has is that in the schematic version, effectively in the schematic version, it has power, and in the layout version, it has VDD. That's it, one error. So I'm pretty pleased with that because that means it's treating all of the other exports correctly. It's recognizing our 3 transistors in parallel. All that matches up. All of the size match up. All of our technology matches up. So that's a pretty solid bit we have there. So I think then that if you guys can finish up the schematic representation of our transistor. then we are done designing our reference current mirror, which is actually, I know it may seem like a small thing, but that's actually a very, very large step. Because our differential amplifier is going to be biased by this exact circuit.
For your grounding rings, Dr. Hardman, did you use like active regions or wells?
So those are, if we go to the components, so for the grounding rings, I used well for P well for this guy on the bottom and N well for the guy on top.
Okay. Is there a reason that you did wells instead of, say, like using active regions?
So because P well is a connection literally to the P well. So it puts, so what this guy is, if I drop this on here and we zoom way in on it, okay?
Mm-hmm.
Zoom way, way, way in so that we can see everything. All right. So this outer area with the brown diagonal lines, that is P well. Then this yellow region where it has the diamond shaped pattern, that is the select layer. So that is N select. The fluorescent green bit right here is N, hold on, sorry, so this is P select, this is P active, so it's making a P plus implant that is connected to metal, which is the darker green area, because when you put the blue metal on top of the light green, it looks like this, and then in the middle is via. And so we have to use the well connection for our bodies because we are trying to connect to the P well for the Nmos transistors so that we can bias our substrate to be at ground. And we have to use the N well for PMOS transistors because the local substrate of a PMOS transistor is an N well. The active, if we looked at P well versus P active, it's significantly different because this is sitting inside. So the region on the outside of the select and all that kind of stuff is N well. So we have to use, excuse me, we have to use the P well contact, or we have to use the well contacts for the body connections and the active contacts for our source and drain connections. Because we're not trying, we're intentionally not trying to connect to the substrate when we're trying to connect to the source and drain. And when we're trying to make our body connections, we are intentionally trying to connect to the substrate.
Okay, I guess that's where my misunderstanding is, because I thought it was like for an Nmos, you would go from the P substrate to a like P active to metal, but
this might be easier. Let me draw a side view of what's going on in
Okay.
that other thing. No, not Zoom. What? Okay. Let's see. So much stuff. Engineering paper. There we go. Move this out of the way. All right. So we have that's the top surface of our substrate. Down here is the bottom surface of our P-type substrate, right? So if we want an Nmos transistor, we are going to have an N plus region over here and an N plus region here. So like when we draw, let me be clear about this. Let's see. Then on top of that, and I'll draw it in yellow. So that active region is the active layer by definition is what cuts holes in the field oxide, right? Our select layer is larger than that so that we don't run into alignment issues. So that's what that yellow layer is just the select telling us where we're going to dope. Then we have our vias. And then we have our metal 1. For our transistor bit, we have our gate here in the middle, and that's why here's our gate, and then there will obviously be, dang it, a via, and then our contact to metal 1 or metal, might have to go from metal 1 to metal 2, whatever. So that's how our transistor is laid out. And this guy right here, this whole structure, this is an N-active structure, okay? For our body connection, we are going to need a P plus region so that we don't form a diode between this guy, this area, and our substrate. Right? We intentionally want the PN junction here, right? And here, because that's how our transistor works. But for this guy, we implicitly do not want our PN junction. So we have a P active region. We have P select. Then our via. And then our metal 1 layer. So this guy is a P well. Let me go back to electric. Yeah. So that's what the P well looks like, and that's what the N active looks like from a side view.
So if this was a like not a P substrate, the P well would then be a P active. Is that
so?
Like the only difference between those two, inactive and P well, would be the substrate and like the region.
Yeah, what's connected to the substrate, right? So if we did a PMOS transistor, and this might help clarify things a little bit. We're still going to do it on a P substrate because that's what we have, but then we have,
N well.
Yeah, a big, huge N well. Then we would have our P plus. select via metal 1. We're going to have another one of those that's going to form the other. If this is the source, then the other one will be the drain. You know how that goes.
And that would be a P active, right? Not a P well.
Exactly right. Yeah. So this guy is a P active. And then to make our substrate connection, we have an N plus N select via metal 1. And this guy is our N well.
Okay, that clears it up.
Yeah,
Quite a
so
bit.
this guy is forming the diode, and this guy isn't.
And the little well, say like with the P plus in it, like not the whole thing, that would be like an active layer.
Yeah, so you're talking about this guy right here?
Yes, sir.
Yeah, so that's formed by the active layer. Yes, the definitions of that P plus area inside the N well is formed by using the active layer.
Okay, I think I was getting active layer and P active and wells and stuff all confused. So that
But-
I think clears it up for me.
All right, cool deal. Any other questions about what any of this jibber jabber we're doing means? I know it can be a little, it can definitely be confusing because you're thinking, you know, okay, so I got an Nmos transistor, everything's supposed to be N except the body connection because that needs to connect to the P well, and it's not remotely intuitive. You really have to think about, oh God, do I want a diode or do I not want a diode as to what you put where? Which can be cumbersome. All right, so let me delete these two guys. They're unnecessary. All right, so how are
Okay,
you guys?
question with this?
Sorry.
Sorry, I'm asking all kinds of questions today.
Oh, that's good. I
For
would
the
much rather
top,
you guys actually be engaged and ask questions of me than me just rant for 2 hours. So,
okay, so for the top gate, like in that setup,
okay.
you have it like all on the top
Uh-huh.
of the transistors. Would it be better to connect it across like the bottom between like the first and second transistor across the bottom? So it's only crossing at that one spot and then across the top?
So you're saying effectively make a serpentine type thing.
Yeah. So I kind of mirror what the other things are doing, but like the metal runs are doing, but not.
Yeah.
Like, would that be less capacitive, I guess?
So I am concerned that if we ran all of those effectively in series like that,
It'd be longer.
yeah, that it would treat the transistor as a long length one as well. And so that's the beauty of being able to simulate all this crap, is that we can literally find out how it's going to behave. So let's do just that.
I actually meant the other way, but I mean, I guess that would work
Okay.
too.
No. Nope, I see what you're meaning. Let me delete this guy, delete that guy. And then,
The metal would have to
yeah, I'll
reconnect.
reconnect the metal in just a second. I was just trying to see if I was going to have
Okay.
errors. So let's see. That's correct, right? Yeah. Drain, drain. Okay. See if I get any errors. No errors. Tools, simulation.
You didn't put your region back either.
Yep. Well, it didn't give me any error, so I don't think that would have mattered, but thank you.
Okay.
All right, so let's add ID M1. Looking like I can tell right off the bat it's had a pretty significant effect because it's close to negative 0.1 milliamps, which means probably somewhere in the order of 90 microamps, but let's just check. That traces ID M2. No, I stand corrected. It looked like it was going to be big.
So it didn't really change anything.
Yes, it does not appear to have changed much of anything. So that seems perfectly valid.
Okay.
I think the reason why it's not treating it as a long length transistor, if we had deleted these contact areas in the middle, to where we're forcing this bit to be like, hey, this, you know, if this is the source, then we're forcing this bit right here to be the drain. If we didn't have those, it would treat this serpentine pattern as a long length, I believe.
Okay.
But yeah, that appears to work. So sure, that floats your boat. Go for it. Because it does, like exactly what you said, it does make the parasitic capacitance seems like it'll be smaller because we don't have as much area of overlap between the metal 1 layer and the polysilicon 1 layer. So seems like a reasonable change.
And probably the last question that I have today.
Okay.
For like fringe capacitance,
Right.
so let's say that gate you have between the second and third transistor and that VDD metal, would there be a fringe like on the overlap right there?
This area right here.
Yes, sir.
So there's always going to be fringe capacitances. It's just a question of are they significantly larger than the area capacitance? And so let me pull up the table from you guys' exam.
Could you pull up the exam too? Because my question specifically refers to the homework or not the problem we had on the exam.
All right, exam 1. So let me move this out of the way so I can see. Page down, page down, page down, page down.
Okay, so for the metal on the left, like
Yeah.
I feel like it's pretty clear there's a fringe capacitance between it and the substrate for like the 3 sides.
Right.
But for the side that overlaps with the poly, like would there be a fringe capacitance there?
So there's like I said, there's technically always going to be a fringe capacitance. So the issue here, and I think I can guess what you're getting at. So I'm going to go down to the table.
Okay.
So you're looking for metal fringe from metal 1 to poly, right?
Mm-hmm.
So yeah, so it says that there's 69 attofarads per micron of fringe capacitance between that polysilicon 1 layer and the metal layer M1. So let's go back.
What about metal to substrate right there where the poly is?
No, because
okay.
But there will be, okay, so how this, I'm going to draw, let's see, that's poly 2, right? Oh, let me open up this PDF and that other thing so that I can draw on it.
Okay.
All right, so I'm going to draw exactly what I'm looking at here. So I'm looking from A to A prime. So here is the top of my substrate. I'm trying to make this just as long. Okay. So here's my thin oxide layer. So here's my substrate. All right. Then in this region right here, I have this big old piece of poly, right? And it forms a capacitance with the substrate.
Yes, sir.
Then I have this guy right here. That's my poly 2. And it forms a capacitor with poly 1.
But it wouldn't form a capacitor with substrate.
Correct, because effectively it's blocked by that big shielding thing of polysilicon 1. Then over here, I have a via, and over here, I have a via and a via. Then I have that's my metal 1. So I'm going to have a capacitor from here to my substrate. I don't know why I drew that one in brown, but that's fine. So that's from metal 1 to the substrate. Then over here, I'm going to have a capacitor from metal 1 to poly, and from here, metal 1 to substrate.
Mhm.
All of them will potentially have fringe capacitances just based on the perimeter of the area of overlap.
Okay. See, that's the part I'm shaky on.
Okay. So like I would consider, and I'm not gonna get like super crazy granular about this because this is I don't have any real evidence other than my experience and how I'm thinking this would behave. So effectively, I'm treating this chunk here as 2 separate pieces of metal that form the plate of those 2 capacitors,
Mhm.
right? So I would take the perimeter of this guy, which is going to give me the fringe, and I would take the perimeter of this guy, which is going to give me the fringe for this one.
Okay.
If you only did 3 sides, I understand the logic behind that, because if we look at that capacitor, we're going to see field lines that are going to extend into that region, and it's awkward. So if you only did these 3 sides, I wouldn't even really consider that wrong. It's just not the way that I'm looking at it.
Okay, I think I did all 4 sides. I was just unsure because like I know Fringe is like when it kind of bubbles out. I didn't know if it would do that over like those weird sides. So
Yeah, no, and that's reasonable. And the answer to that is I honestly don't know. I mean, that's the reason why, like, our parallel plate capacitor equation, epsilon A over D, technically is only valid for an infinitely large set of parallel plates, because the way that the fringe capacitance behaves is so poorly defined.
okay,
So we're just making our best guesses here. I can't
Perfect.
fault you for doing anything but that.
all right.
Alrighty, any other questions about stuff? We got 3 minutes left.
What
Alrighty.
everyone else says, I think.
Okay, never mind. I lied. I have another question.
Okay.
For the problem right before this. Never mind. Right after it.
Yep.
We're finding the time delay, and in the book it has like unit capacitance times unit resistance times L squared, which is just RC. And when you did it in class, I think you did the same thing, but you also talked about like doing a geometric series and finding like n times n plus 1 over 2 times the RC value.
Yeah. Okay. So you're asking what the difference between, there was one that was like the delay time is R squared times the number of squares. No.
R squared times 1 square times length. And then C square times 1 square times length, which would be like R per unit length times C per unit length times L squared, which was like what they had in the book. Yeah, RC. And then when we derived it in class, we got natural log of a half, some stuff. And so that was 0.7. And then I understand 0.35 is half of 0.7, but I don't know where that half came from except from the geometric series part. But I didn't use the geometric series part, so.
Okay. So, well, I asked you specifically to use the distributed parameter transmission line model, which would have been this guy.
Shoot.
It's okay. So the thing here is R total is R squared times the number of squares. And C total is C squared times the number of squares. So this guy is just going to look like 0.35 R, R square C square N squared, which is taking account the total number of squares squared, and this guy is N times N plus 1. When there's a whole bunch of squares, these two numbers are effectively identical. When it's a short transmission line like this one is, only 10 squares, you could find out what the difference is going to be, and it's going to be probably less than 5%, but still appreciable. So I'm not going to be like, oh, you did it wildly wrong, you lose all of the points or anything like that, but it's a less exact answer.
Okay.
So that's it, yeah. All right, it's 9:50, so I will catch you guys on next Tuesday. So Tuesday is election day. I don't know how early the polls open in Minden, so I might be a little bit late. but I will be on as soon as I possibly can.
Dr.
That's good.
Hartman is advising in person or in Zoom?
Whichever way you prefer. I sent out the link to my Zoom office hours, although you would have it because you're in one of my classes right now anyway. Or you can drop by in person, just whichever way floats your boat.
Thank you.
Yep. Any other questions before we get out of here? All right. Catch you guys on Tuesday. Thank you.
Have a good one.